Well, welcome to the video that deals with the differences in the way you have to fertigate uh, depending on the irrigation method that you have. And there's some major differences. As a reminder to all of you, including people who may just popped in on this one, uh, these videos are, this whole video series with 24 videos really is a supplement to the fertigation books that we have, either in Spanish or English. And so, of course, the videos are also in Spanish. But that's where you will really learn the information. These videos are meant to stimulate your interest and sort of explain things. And if you want more details, you go to the book. Some of the 24 videos are not lecture format. Instead, they deal with videos that we shot in controlled conditions in a laboratory or out in the field in some cases to show you how things work, like injection equipment and that, and a lecture isn't sufficient. So we did it that way. Of course, you may just be dealing with one irrigation method, like a center pivot or a drip system, and that's fine. Some farmers deal with multiple irrigation methods, or they may hear about how people do something with a center pivot, and they may surface irrigate, like with furrows or border strips, and they have to realize that they can't really just take everything directly and apply it. So you have to fertigate things differently. An associated statement is, if you want to fertigate properly, you have to make sure often that the first thing you do, and this is a repeat of what's been said several times, you have to make sure that you have a high DU. This is especially true with surface irrigation, which is often, unfortunately, well, it's managed with a poor DU, and therefore you would get poor uniformity of your fertigation also. So we'll move on to the different methods. I like to classify um, irrigation systems for the purpose of fertigation into two general categories, and they might surprise you. It's not sprinkler and surface or drip and sprinkler. Really, the two categories that I use to sort it out in my head are one type of irrigation systems move, and that's a continuous move, and another is stationary. So here's a list of continuous move systems. Center pivots, they move all the time. Linear moves, those are easy to understand. Travelers, like big guns that are hose reel, that sort of thing. Those, as opposed to being on a grid, those move continuously. Furrows move continuously. The water advances down a furrow. It isn't at the same place all the time, at least the head of the water stream, and then the way the water goes into the ground changes with time. So that's sort of a moving target. Same with border strips and basin. So these are all special categories. To me, the stationary ones are not ones in which you never move the equipment, but rather while you're irrigating, they stay in one spot. For example, solid setter is easy. There's a grid of sprinklers out there in your field, and you just don't move anything until you pull the whole system out. Hand move, the sprinklers will sit in a location for perhaps 12 hours or 11 and a half hours, or 23 and a half hours, something like that, and then you'll make one or two moves a day. Wheel lines are almost always moved twice a day. Drip is stationary. When we started with drip, there was an idea of moving it around, but basically it just sits there. Same with micro sprinklers and micro sprayers, and permanent under tree or vine sprinklers. Those are obviously stationary. On the moving sprinkler systems now, so I'm combining two ideas. One is it's moving, and one is that it is a sprinkler system as opposed to surface irrigation. The pivots, of course, have end guns, end sections that may come on or off on the corners. And in that case, the flow rate changes, and you need to have proportional fertigation to get the proper ratio of water and fertilizer. The other thing is, on moving sprinkler systems, where they're in a different spot every time, you better be fertigating all the time. You don't want to stop fertigating short of a complete rotation, for example, or just kind of go on and off. There'll be gaps in the field where no fertilizer is applied. Hopefully that makes total sense. And here's another thing, it's sort of related. It's one of these things that I run into a fair amount. It's this. when you're fertigating and also when you're irrigating, I hope you're thinking that that water is going in the soil. Well, that doesn't always happen on these moving systems. If you move a system too fast and you just apply a very small amount of water, that water won't get past the leaves and the soil surface, and then it evaporates out. You actually have very high evaporation rates. And people notice that their field is drying out, and they even speed up the machines, which is the absolutely wrong thing to do. You basically want to operate as slowly as possible without having runoff. And that allows the water and the chemical to get into the soil and below the soil surface. I'm going to start with a section on surface irrigation, and for some of you it may not be interesting at all. That's the way it goes, but for others it's real important. They're difficult to understand, so I'm going to, well, I don't know how simple I can make it here, but I'll give it a try and have a few graphs. But the first thing is, this is entirely different from sprinkler drip because the soil itself controls how the water moves across the field and how it infiltrates into the ground. And the problem is the way water infiltrates into the soil isn't constant. So you're out of control. In other words, you don't have the control. You can notice what happens, and you can make appropriate changes, but you don't control it. It's not like pipes with drip and sprinkler, where we know how water flows through pipes. We can calculate friction, elevation change, all that. Everything's predictable. It happens the same time every time you irrigate. Surface irrigation systems are a moving target. Remember, like in the little image behind me, if you look at it here, those are furrows. Water is covering, in this case, it looks like about 50% of the area. The water is advancing down the furrows. You can see the water's getting into the furrows via siphons. There are many ways to do it, many different furrow spacings and so on. But the bottom line is it's not being conveyed down the beds with pipes. The soil is dictating how fast that water is going in, and also how fast that water advances down the field. And the infiltration rates, in other words, are the key thing. The problem is they change from minute to minute, and also from irrigation to irrigation. In other words, you have different infiltration rates at the beginning of the season and the end of the season. You have different infiltration rates at the beginning of an irrigation and the end of an irrigation. So I'll try to show you some graphs that hopefully won't be too mind-boggling to explain it. First of all, we have a term called opportunity time, and the opportunity time is defined as the total time that water sits on the soil surface at a point. So we kind of say, okay, let's forget about the whole furrow. Let's just look at a point. How does the water go into the ground? And the opportunity time then is the difference between when the water gets to that point and when it's no longer standing on the surface. That difference, in other words, when it disappears. That's the opportunity time for infiltration. And the thing is if you had an identical soil all the way across the field, you would like to have the same opportunity time, because then you would have the same amount of water go into the soil at every spot in the field. But this is like pressure differences with sprinklers. Opportunity time differences are equivalent to pressure differences. And I mentioned in another video that just as we have PC emitters, or pressure compensating emitters, where the flow rate is about the same regardless of the pressure, we do have some cases with cracking clay soils, such as in the Imperial Valley, that will infiltrate a certain amount in big cracks. They basically fill the cracks and then they stop infiltrating. So there are those cases, but the majority is not like that. Chapter 7 has these graphs in it, and you have to look at them real carefully. Let's start with the top one. First of all, on the horizontal axis is opportunity time in hours, and just 10 hours as an example. And don't worry about the exact numbers on these things. These are just to give you the idea. Second thing is, on that top graph, there's 3 different soils, just to conceptually show you what happens with different idealized soils: a sand, a loam, and a clay. And then the vertical axis is cumulative depth infiltrated. For example, if you look at the sand, the way that graph shows, it shows it after about 10 hours. It's 10 on the horizontal scale. The vertical scale shows 20 inches. That's a lot of water, but the idea is that the sand, this particular sand, would infiltrate 20 inches of water in 10 hours. And if you notice, this is not a linear graph. In other words, a lot of the water goes into the sand at first, and then less and less goes in with time. But this is cumulative, so inches. The next graph, the one below that, deals with this idea of rate, which is different. Same soils, same arrangement, sand, loam, clay loam. This says clay loam instead of clay, but it's the same kind of idea. And this is the infiltration rate. And this says, hey, look at, on a clay loam, for example, you might start out when the water just starts infiltrating at a fairly high rate, but the rate at which water goes into that ground drops quickly. It's kind of like the speed, you know, like you're going real fast at first, and then you slow down, and then in the end, you're more or less going at a constant rate and fairly slow. All of these more or less taper down to a fairly constant rate, but they're different constant rates. In other words, the sand maintains a higher constant rate or basic intake rate than a loam, than a clay loam, conceptually. So there's this change, and this is what I meant by these numbers change with time. It's not like sprinklers. With sprinklers or drip, if you irrigate twice as long on a spot, you get twice as much water in the ground. With surface irrigation, if you irrigate twice as long on a spot, this is just a spot in the ground, you may get 50% more, not double. You see, because these are curves, they're not lines. This second one shows you that not all furrows and surface irrigation are equal. Again, it's a general concept I'm trying to get at here. You notice on the bottom right, those are furrows. Every other furrow is irrigated. And just imagine if you had every furrow irrigated, you'd have twice as much going in the ground. I mean, hopefully you understand that, you know, if you have twice the area that's wet. Same field, same soil, irrigated differently. It's kind of a no-brainer. You irrigate twice the soil, you get twice the amount in the ground. The border strip on the left, or basin, you know, depending on exactly some of the details in it, that happens to be a border strip. In that type of thing, see, there's a small grain on that crop, and they put in huge flows into these wide basins, and the water flows across like a sheet and covers everything. So the difference is shown in the upper right hand side here on intake rate. You see a border strip has a higher intake rate than a furrow, and these are just conceptual here to give you an idea. Why? Because a border strip has the whole area covered with water. So you actually have trouble getting much water into the ground with furrows if you don't have it sitting there for quite a while, simply because you have a small area. Border strips, on the other hand, you can get a complete irrigation certainly within an hour or so at a point with a border strip, where it may take several hours with a furrow. Here's a classic case, believe it or not, of what happens with many people with furrow irrigation, and which is why they get lousy results when they fertigate. It's not due to furrows itself, it's the way they're irrigating. And this is mentioned in another video, but what this graph shows here, if you take a look at it on the horizontal scale, there's the length of a furrow. So this is about a quarter-mile furrow, 13-20 feet, if you notice. The curves and line, you know, they stop there. And then there's a thing here, advance time. And the time here that you have. So what you have is a at the head of the furrow, this shows, well, okay, the water was applied for about 24 hours. See, it says 24.1. But that means, okay, siphons or gated pipe were supplying water to the head of the furrow for 24 hours. And what irrigators do is they learn over time, there are not any books that you can use for this, they learn over time that if they put a certain flow rate down this furrow at this time of the year with this soil and this slope and this crop, so this is really kind of tough to learn, but if they do it, they'll get it down there to the end of the furrow, 13-20 feet down, just maybe an hour or two before they have to change the water to the next set of furrows. See, so what this shows here is they got the blue curve there as the advance. The water went down, it zipped along pretty fast, and then it gradually kind of tapers out. It takes longer and longer to get to the very end. And it got to the end here in about 22 hours, something like that, about 22 hours. Then, so that irrigator for many farmers, man, that was a good irrigator. In other words, the water just got to the end and maybe he dammed it up a little bit, or there was just a little bit of runoff, see. Now, at the top of the furrow, when you shut it off in 24 hours, the water still sits there for a little bit of time. That's why it says 24.1 hours is the opportunity time, because water is still sitting there another tenth of an hour. And you notice that line, that orange line, is not horizontal, the recession line. That's the time at which water disappears from the soil surface at various distances down the furrow. And so this particular graph shows that, okay, the opportunity time at the end of the furrow, that's the difference between when it got there, when it disappeared, was 2.2 hours. This is an obvious case of non-uniformity. I mean, just go figure. About 24 hours at the top, about 2 hours at the bottom. There's just no way that you're going to get about the same amount of water in the top of the field as the bottom of the field. And the fertilization is going to go in just the same way. Now you can play all kinds of games and tricks and not put the fertilizer in at the very beginning, and it's just very, very complicated and doesn't work very well. There are ways, of course, to get water down to the end of the furrow much faster, so it doesn't sit at the head a lot longer. The numero uno, the big one, is having shorter furrows. That makes a huge difference. And the bottom picture shows intermediate gated pipe. That's what we call it. See, there's no road there. The gated pipe is put out there and across the middle of the field, and effectively cuts the field in half. Water from the upslope side on the left just goes right under the gated pipe, and it moves on down the field. And then you normally irrigate a group of furrows from both the top and the bottom at the same time. So that is absolutely the biggest thing that you can do. The image on the top up there shows what we call a torpedo. It's dragging behind a tool bar, and you know, in furrows we have wheel rows and non-wheel rows, and the non-wheel rows are the ones where the tractor tires don't go down, and they're kind of fluffy and have higher intake rates than the wheel rows. And it's a common practice in some areas to compact the non-wheel rows, the ones with the higher infiltration rate. You compact them by dragging these weighted torpedoes down. They're filled with concrete. You know, you can see it's just hard-faced, so it doesn't wear out. And you drag them down. It really reduces excessively high infiltration rates on a lot of soils. And of course, if you use a higher flow rate per furrow, you can blast the water down in less time. With surface irrigation, you can usually get a good DU. That's distribution uniformity. If you have a ratio between the maximum opportunity time and the minimum opportunity time of about better than 3 to 2, or this expresses it differently. This is a low to the high. In other words, you want the numbers to be kind of close. And that just doesn't happen in a lot of places. It means there's tailwater a lot of farmers can't have. They don't want to have any tailwater. Tailwater return systems get very expensive with very small fields. They're more economical on large fields where you can take the tailwater from one field and maybe use it on another field. And remember, there are pumps on these things. So there are legitimate reasons that people have, but bottom line is they're not going to have very good uniformity and easy management in a lot of these cases. So on the left, there's a big tailwater return system. You know, you can see it's a pit that goes a long ways. It services multiple fields. On the right, there's a smaller one. You see less and less of these around as people shift more to sprinkler and drip. But that's what tailwater return systems look like. The water flows into these by gravity, and then you pump out and you go somewhere, either to the head of the same field or to another field. The one on the left actually is big enough that it can supply a whole field or several sets in a field. for irrigation. And some places you see they're very commonplace, and other places you never see them. Again, this is a topic which some of you have no interest in, but for furrows, this is not intuitive, if you're irrigating with furrows. This figure illustrates how water infiltrates along a furrow as the water advances. Now, if you take a look at it, this is the graph here on the top shows the head of the furrow and the tail. And so that's a distance along the furrow. And there are three curves here. One is T1. T1 says, okay, we have irrigated at this moment in time, we've been irrigating, let's say for 6 hours. Let's say that's T1. And maybe the water got halfway down the furrow in 6 hours. And what happens, of course, is right at the halfway spot, there's no water. Water's just getting there, so it's just starting to infiltrate. And quite a bit of water has gone in at the head. Remember, the initial intake rates are pretty high. That's what's called a non-uniform irrigation, simply because there's not even any water at all in that downhill half of the field. T2 there shows the condition where you've been irrigating longer and the water has reached the end. Now, T2 has got to be much more than twice T1, simply because the water advance rate slows as it goes down. So if T1 was 6 hours, T2 might be 18 hours, just to give you an idea. Again, that shows quite non-uniform irrigation. You just barely got any water in at the tail end and quite a bit in at the head end. But you see the rate at which the water went in at the head end, it slowed down considerably. See that? You didn't get that much more water in at the head end. And then T3 indicates you continue to irrigate for more time, and you got enough water in at the tail end to satisfy your moisture requirement. That's that horizontal dashed line. And you got extra water in at the top, but not that much extra water. So that, of course, if you compare the curves for T1, T2, and T3, T3 actually has a very good uniformity. But all the time between T2 and T3, you have runoff, and that's where people kind of choke on it. It is a hassle, there's no doubt about it. So now this is for surface irrigation. First of all, hopefully you understood some of this. And what I'm telling you is you forget good fertigation if you have a poor irrigation system to you. And if you're into furrows and border strips, you might realize that you might have a long ways to go. Just so you know, I don't have enough time to go over this, but the border strips can actually be operated with a good DU and with the proper amount of water going in the ground. Those are two different things. With little or no runoff. Furrows, that's not the case, unless you had level furrows. Those are real short furrows. You really blast the water down, and you can do it with that. But let's say you got that down. You have a good DU. You've somehow modified the system. Well, forget these rules like start injecting when the water's advanced halfway down the furrow. It's just way too complicated. Instead, what you do is you inject fertilizer at the head of the field at a constant rate. In other words, this assumes that the flow rate coming into the field stays the same over time. And you inject as long as that external water enters the field. And in other words, you start when the water comes into the field, you stop when the water stops coming in the field. And that does not include tailwater. It turns out when the tailwater, if you have a tailwater return pump and you're blending that back in at the top of the field, that tailwater already has the fertilization in it, the fertilizer in it at the proper rate. So you don't have to worry about any extra computations. You don't have to adjust the fertigation rate. So basically, it's pretty simple. You inject at the head of the field the whole time water's coming into the field, except for the tailwater, and the tailwater just takes care of itself. Now, I'm not saying that surface irrigation is easy. There are farmers who do a very good job of surface irrigation, and there's some that, quite a few that don't. I've given you the idea of uniformity. You basically need uniform soils, and you need uniform infiltration rates, and also you basically have to have good advance ratios. In other words, your opportunity time ratios. But then there's the problem of are you putting the right amount of water in the ground? And because that's going to dictate how much fertilizer you want to apply. And basically you're saying, okay, I want to put on so many pounds of fertilizer here, and you just can't go to a book again and learn that for this particular soil out here in this field with this crop and this slope and all that, there's no book that gives you the right answer that it's going to take you with 2,000 gallons a minute or 4 CFS, it's going to take you 23.9 hours to irrigate this field. There isn't anything like that. So you have to go and look at your records. And remember, the amount of time it takes to irrigate a field depends on the infiltration rate, which depends on how your furrows were formed up or border strips were set up and the time of the year. But if you have good records, you will know that for a certain flow rate, you can finish off a field in so many days or so many hours. So here's a simplistic example. Let's just say that you know that to get the irrigation done here on this field, it'll take 100 hours. Don't worry about the exact number, just this is an example. And you want to apply some amount of fertilizer, in this example, 20 gallons. Well, your injection rate at the head of the field is, and this is relatively simple, 200 gallons divided by 100 hours is 2 gallons per hour. That's how you do it. And you adjust your injection rate. With stationary systems, there's a lot more choice. Basically, you have two choices. The first one looks like two choices, but it says you can just fertigate continuously and proportionally. Remember, those are two different things, but in other words, when you turn the pump on, your irrigation pump or turn on the valve, you're fertigating at the same time. When you shut it off, you stop fertigating. And that works very, very well if you do it continuously. But a lot of people want to have it very simple. There's nothing really inherently wrong with this if they do it frequently enough. They wait until the hoses and pipes are full, and then they start fertigating and stop early enough so that all the fertilizers left the hose. It can have problems. Primarily, I think it's primarily with the labor. That's the biggest problem. You have to have people kind of hang around and that sort of thing. And but it definitely doesn't require PLCs. But there are extreme cases. And I've seen this with people who have drip irrigation in greenhouses, for example, or in smaller plots. And they may have dozens of these plots. And they may want to apply some special mix to a particular greenhouse or a plot. And so, I'm standing there and they say, okay, we're going to start irrigating this plot. So they start injecting back at the pump. And then they stop irrigating that block and they stop injecting at the pump. Well, the problem sometimes is that fertilizer is still in transit. It hasn't even reached the plot yet. How's that? In other words, there are travel times through main lines and submains, and so then it gets really complicated. In fact, you can really do a horrible job that way. So if you're really looking at these short times and bouncing things around, I really think it's better to inject, and easier actually to inject proportionally and continuously and not worry when things are turned on and off. This assumes it's all the same crop and that. Otherwise, believe it or not, what some people do when they have a lot of small plots is they actually have portable equipment and they take it out to the individual plots and they will frequently inject the required amount of fertilizer. Some people even give their irrigators a schedule every day. Okay, you irrigate this block for 2.5 hours and you put on this many units of N, nitrogen. and so they kind of spoon feed, but they it's more labor intensive, but it's usually a very expensive crop. So back to this half quarter rule where you fill up the lines, wait a quarter of the irrigation time, and then inject for half the time, and then let it go out. That's what you need if you're just really shooting it to it. Large dosages of chemical. Just keep in mind that if you have large dosages that you're putting in, that isn't quite compatible with the way plants take the nitrogen, at least that fertilizer up. Anytime you have large dosages, you have possibilities of precipitation of chemicals in irrigation water, and then you can also get toxicities. So anyway, it's not the perfect thing. So this is what I was talking about regarding when you have a lot of small blocks, where people have a trailer or they put out a tank out in the field at each block, that sort of thing. And it's definitely an option for stationary systems. You may do this in a variety of ways. You may decide, for example, that chlorine and acid need to be applied everywhere. And so you may have a central injection system for those chemicals. But you may think that each crop out there is continually changing within its its growth cycle, and it has continually changing fertilizer needs. And you may actually kind of semi-spoon feed by, like I mentioned before, you give the irrigators a written schedule for each block and say irrigate for this number of hours and this how many gallons of this and that you apply. And again, these are often in vegetables, but I've seen it in large systems with trees with different varieties. For example, you might have peaches, just as an example. You don't usually have one big field of all one variety of peaches, because then you'd have to pick the whole thing in a short period of time. What you do is you want to stagger your picking and your packing, and so you have a lot of varieties of peaches at different stages of growth. So you may actually want to go out and have injection points out in the field, and it's not as complicated as it sounds if you have the right instructions and the right injection setup. Normally, since the lines are pressurized, the irrigation lines are pressurized, when you go out there, there's a self-flushing when you open a valve. So you let some water flush out onto the ground. Then you shut the valve off, hook up your system with a quick coupler, and then inject what you want, and that's it. And again, keep the dosages relatively small. And for more information, we have a lot of things on our website, www.itrc.org. Just make sure it's ITRC, not IRTC. It's a common flipping that people do. It's ITRC. So have a good day.